Hello physics, this is going to be my version of a review for our electrostatics and Coulomb's law kind of test. So key ideas to remember: like charges, so that would be if I have two things that are positive or two things that are negative are going to repel, and opposites, charges, attract. Okay, so I feel like we probably knew that, but let's dive in a little bit deeper into how are these charges being made? How do we get something that's negative charged? How do we get something that's positively charged? And we have three ways of charging. Okay, so first one is charging by friction. So this would be literally I'm rubbing something against something else. So I rub, I think in one of the videos I talked about rub my socks against the carpet, or you could rub a glass rod against a fur. And when you're doing that, it's literally going to be electrons moving from one thing to another. So from one material to another. And usually, well, not usually, always, whichever one is going to be gaining electrons, I'm going to say the electron gainer, the one that is taking the electrons, becomes negatively charged, and the electron loser is going to be positively charged. Okay, so that's charging by friction. Second type, charging by contact. And yes, I realize when things are rubbing together, charging by friction, they're also in contact, but this is a different thing with an annoyingly similar name. So by contact, we're looking at a charged thing, already charged one way or another, touches something else. And so whatever charge that charged thing has is going to kind of be distributed among the two things. So this was, I'll throw up this example from the other day. So I had this charged rod. It was negatively charged. When it touched this metal sphere, its charge, so I have all of these electrons. Some of them flowed into the sphere. Some of them would have stayed on the rod. You notice this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like 11 negatives, and only 6 of them hopped onto the sphere. So when while they were touching, the rod and the sphere would have had equally negative. The charge would have become spread throughout them. I'm going to say charge spreads. But one thing to still think about, even if the charged thing was positive, yes, when we're done, both things are going to be positive, but it's not the protons that moved, it's the electrons that would have moved into the positive thing. So again, this is just kind of like what we had. So this was positive, and so when they touched, when they came in contact, the charge was spread between them, but it was because electrons moved. Remember, electrons are the only ones that are really mobile. So the electrons moved in, and so we end up with a positive thing because of contact, but it's electrons that moved. And then third way something can really get charged up is charging by induction. And so when we're charging by induction, we have a charged thing brought near, but not touching another thing. Okay, so I have something, just whatever it is, that has a positive charge. I'm going to bring it near maybe one of those spheres like in that picture. Okay, so right now this has no charge. It has positive protons and negative electrons. Remember, the electrons are mobile. The electrons can kind of move around. So if this is really positive and it's brought next to this, okay, remember the electrons in here can kind of move around. So are they going to try to move towards the rod or away from the rod? Okay, well, opposite charges attract. So the electrons are going to kind of move and be more over here. Okay, the positive protons are still everywhere. They're spread evenly throughout. They don't move. But if I have a bunch of electrons move over here, I'm going to end up with a negative side and a positive side. So this thing has been charged by induction. It's become polarized. It has a negative end and a positive end. And then the idea is if I then broke this apart, I'd have a negatively charged thing and a positively charged thing. But the idea is induction, they don't actually touch, right? It's just that electrostatic either attraction or repulsion that causes the difference in charge. And then the last thing that we really have in this chapter is Coulomb's law, which I never spell right. Yep. Seems like there should be another U in there. Which is the force between two objects equals Coulomb's constant, and then the charges between them and the distance squared. Okay, so let's just go over units real quick here. So force, like every force we've had so far in this entire year since August, is going to be in newtons. The Q is representing charge. We measure charge in that strange little tiny baby unit called coulombs. D is for distance. Again, just like every time we measure distance in physics this year, we're going to use meters. And K has its big fancy unit that I don't care necessarily that you write out, but it is Newton meters squared per Coulomb squared. And the unit actually makes sense because it is, I'd have coulombs times Coulomb, so that's Coulomb squared, and distance squared. And so if I was isolating this, I would be multiplying times meter squared and dividing by Coulomb squared. So the unit makes sense, but it seems a little cumbersome for our purposes. So remember, if we calculate a positive amount of newtons, that means our two charges were the same, right? It was either a positive times a positive is a positive, or it was a negative times a negative is a positive. So they'd have the same charge, which means this is a repel. And if we calculate negative newtons, that means one charge was positive and one charge was negative, so this would mean those attract. The coulombs, you're going to see a lot of problems where these are really, really small numbers. And so just kind of have to think, if they're really, really small forces and they're going to have small charges and they have to be really close together, or we can have them all big, just kind of trust your numbers on that one. Okay, so if you need to actually calculate this, then might as well plug in. Remember, this is always that same number, 9 times 10 to the 9th. You would always plug this in for K all the time. Okay, but there are a lot of questions where they don't actually say calculate exactly the charge or calculate exactly the meters. They say what would happen if we doubled this or we made this half as much. So remember, that's when we use that kind of, we substitute in numbers compared to what it would be if it was 1. So maybe if this original force was, the original force was 12 newtons, why not? We'll use some big round number. And they say, what's the new force if we double both charges and the distance stays the same? So remember, that is when we kind of plug in double, so that means 2 times. Right, so I'm going to go 2 times 2 for the charges. It didn't say anything about the distance changing. So it would be 4 times bigger. So if it's 4 times bigger than 12, so how do we figure out the actual new force? Well, I would go 4 times 12, which I feel like I should confidently have in my head, but I don't. 48. Okay, so your actual answer, we say if the original force was 12, well, if we double both forces, we have double, so 2 times 2 on the top, so it would have 4 times bigger, and the original was 12, so it'd be 48. So let's try another one of those. New force if, let's say, distance is halved, and one charge doubles. Okay, so remember, this is where we go, we would say, okay, one of the charges doubles, so I'm going to put a 2 up here, the other one is still a 1, distance is halved, it's still 0.5, but it's still squared, so I have 2 over 0.5 squared, which is 0.25. I didn't do this on purpose. 2 divided by 0.25 is 8. So remember, that means it's 8 times bigger. But if our original was 12, we go 8 times 12, so our actual new force would be 96 newtons. I think that's probably pretty good for a review. Let me know if you have any questions, or if you want any more practice to do before you do the quizzes. Again, you're going to get 2 tries at it, so it's up to you if you want to give it a shot and then figure out what you need to figure out, or how you want to do that. See you later.